With that, we can continue to noisy student. The idea is very similar to what we have been covering so far, which is about label propagation. You have some labeled data, you have some unlabeled data, and you want to learn from both of them. It is semi-supervised learning. Using the labeled data, which you can look at this portion of the image now, or this portion of the figure, you have labeled images. This is a canoe, that's a steel arc bridge. You're going to train your teacher model on this labeled data, and you do the usual data augmentation, dropout, stochastic depth, hence the name noised here. You train your teacher. Now you go to the next iteration. You look at your unlabeled data, which are X tildes here. You use your trained model, you use the trained teacher to label the unlabeled images or unlabeled data. This is this box here. You're inferring some pseudo labels on unlabeled data. And whenever you are doing your prediction using the teacher, you remove all of these noises. You remove data augmentation, dropout, stochastic depth, all of them. That's why it is not noised. It is unnoised. Now you have some labeled data. You have some unlabeled data, which you labeled them. Now you can do your training of the student. Your student is going to look at the labeled images. It's going to look at the unlabeled images. For the unlabeled data, it's going to use the labels from the teacher. For the labeled data, it's going to use the true labels. And then you're going to do your optimization. You're going to train an equal size or larger model. And the cool thing about this strategy is the first time that you train a teacher, you have very few labeled data. Perhaps you're going to start with a smaller teacher so that it doesn't overfit, and then gradually increase its size for each iteration in this loop. That's why you're training an equal or larger student. And then the student is going to end up being the teacher. You go back, and then you keep repeating this pattern. It turns out that the noise is extremely important here. Let's see some results. This is the previous state of the art. The paper is from 2020, and the noisy student is doing the best for ImageNet top 1 accuracy. Not only that, this is actually a robust method. There are these 3 data sets, ImageNet A, ImageNet C, ImageNet P, that I want you guys to explore them. These are benchmarks for robustness of deep neural networks. We know what is top 1 accuracy. We don't know what is MCE and MFR. I'm going to explain them. And let's see, at least from the big picture, what is the difference between ImageNet A, C, and P. ImageNet C and P, especially their test sets, these are actually test sets. These are images that went through common perturbations and corruptions. For instance, you blurred them. There is fogging, there is rotation, scaling. ImageNet A, you don't do any perturbation or corruption to them. These are just images that are hard by their nature. It means that, and what do you mean by hard? What do you mean by they're difficult images? The usual classifier networks, CNNs, don't do a good job on them. They're gonna give you significant drops in accuracy. And all 3 of them, ImageNet A, C, and P, these are robustness benchmarks. Let's see some examples. This is ImageNet A. This is a hummingbird. There is no perturbation on the image, but this is just a hard example. And a usual classifier is going to classify that as bald eagle. The true class is a basketball, and it's identifying the parking meter. And the network has reasons to do so. Okay. ImageNet C are fogged, and there is some blurring going on. For ImageNet P, for instance, this plate rack is going to get classified to a medicine chest if you use a usual classifier. Okay, this is about the data. Top 1 accuracy, we know what that is. And as you can see, this is really robust. It is classifying the hard examples really good. It is making less of these mistakes. And the other one, mean corruption error, you're going to show these examples to your classifier, and then you're going to count the number of errors, or you're going to measure the error rate for these corruptions. But then this is going to end up being different from one model to another model. you're gonna standardize that using a baseline. And AlexNet is the first CNN that did a very good job on ImageNet data in 2012. And because it's about error rates, lower is gonna be better. For mean flip rate, you're gonna show these images to your model or any other model, and that model is gonna flip the predictions, like what it is doing here. Plate rack is flipped into medicine chest. You're gonna count the number of times that those probabilities are flipping, and then you're gonna compare it to a baseline, what AlexNet is doing, for instance, as your baseline. And then again, you want less of these flips to happen, therefore the lower is gonna be better. Efficient Net B7 is one of the best classifiers these days. You can compare the number of parameters and the top one accuracy, and noisy student is beating that, especially if you give the model enough capacity, make it a little bit bigger, it's gonna be the state of the art. Okay. Any questions about noisy students? Was everything clear? Okay, awesome. This also belongs to the class of label propagation methods.